Good evening, everyone. Myself, Riya Thomas, PhD scholar from the Department of Physics and Electronics, and here I work under the guidance of Dr. Manoj B. So, today I would like to give a short discussion on the topic carbon allotropes beyond graphite, a cradle-to-gate approach. So, let's say we have an annual carbon compound meet. So, what would be the participants you'll be able to see over there? So it's specifically the major allotropes of carbon. So specifically diamond, graphite, and fullerenes. So what do you understand by the term allotropes? It's a very basic term that we all learned throughout the years. There's nothing but the two or more forms of a physical state in which a chemical element can exist. So when you talk about these carbon allotropes, what is the extreme makeover you'll be able to witness in this carbon family? So that would be the transformation of this black colored opaque graphite material to a very expensive and shiny diamond. So is that the maximum extent of transformation you will be able to see or witness in a carbon family? Certainly not. The possibilities are endless, and it has become more evident with the discovery of 2D layered material termed graphene. So when you consider its worth and also the multifaceted applications, it has actually become a potent contender in the field of material science. And especially when you consider the turnovers in the field of graphene, it has actually become much huge compared to even the most expensive diamond. So as you could see over there, the flow chart, there are many ways that you can extract graphene from graphite. To note that we have chemical vapor deposition, we have a chemical exfoliation methods. So out of all these methods, the most simple and effective technique would be the chemical exfoliation method, in which we have certain steps. So when we look into the graphite, the structure assets, so we have the carbon atoms, which has been arranged in a hexagonal lattice, and each graphene layers are stacked above the one another by van der Waals force of attraction. So how you will extract a single layer of graphene from this graphite? So it's not a single process. We have a multi-step process involved in that. The first step would be the oxidation step, in which we actually intercalate oxygen functional group in between the graphite layers. So what is the advantage of that? So we'll have a loosely bound graphite structures over there. Then by exfoliation, that means by some physical means, what we'll do, we'll try to separate out, or we'll try to loosen out the graphene layers. So in that, what happened, we'll have a single layer graphene with having oxygen groups attached to that, the 2D layered material. So throughout these presentations, I was actually noting 2D layered material. But is that the only configuration graphene can actually constitute? Certainly not. It can have 0 dimension, 1 dimension, 2 dimension, and 3 dimensions. So when you look into that, we have 0 dimension carbon dots. In 1 dimension, we have carbon fibers or CNDs, and 2 dimensional acid like graphene layers, and 3 dimensional architectures also we have. When we look into its properties, it has got exceptional properties, and that has made it to a superior material compared to the other materials in the field of nanotechnology. And also it has got a wide range of applications. So if you look into that, it could actually cover all the broad spectrums, especially it has got applications in the field of energy, ranging to biomedical, environmental, and also to the sensors. But when you want to have this potential utility, when you want to achieve this goal, there are certain hurdles on the way. So to point out some, the expensive precursors, facile synthesis route, multi-purpose applications, production cost, large-scale fabrication, and commercialization. So all these issues can be sorted out to a great extent by the choice of apt carbon precursors. So what are the certain criteria you should keep in mind when you are selecting a graphite precursor? So it will be actually a benefit if you can actually have a naturally available and abundant precursor, because it can help in reduce the cost of the production and also can facilitate a large scale fabrication. And also if we can actually use carbon based samples, for example, agricultural waste, industrial waste, or those waste, and also the naturally available carbon sources like fossil fuel, petroleum products. So if you can actually utilize these products for the synthesis of graphite, actually that would be a value addition. So that's the point actually I come across the fossil fuel, because in a developing country like India, the burning of fossil fuel actually contributes a lot to the air pollution. So the charcoal or the coal, the fossil fuel being a carbon allotrope, and if you can actually extract graphene based materials from coal, it will be actually a waste to wealth transformation. So looking into the significance of selection of fossil fuel as a precursor, as I already told, it is an abundant and a cheap precursor. So here in my studies, I have actually utilized coke, which is actually formed by the high temperature carbonization of fossil fuel coal. So it has got pre-formed graphitic clusters, which helps in the easier exfoliation of graphene. And also it is known to be the highest quality coal. So in turn, what helps? It helps in the production of high quality graphene system. Also, it has got enhanced graphitization and crystallinity, which is very much, beneficial for the electrochemical applications. It also got many much defect size, which can actually serve the purpose of active size, again beneficial for fluorescence or electrochemical applications. And thus, we found that if we can extract the graphene from fossil fuel systems, it can actually would be a value addition to the product. So considering these facts, we actually synthesized oxidized multi-layer graphene from coke, and the work has been published in the Journal of Materials Chemistry and Physics. So here we have actually followed improved Hammer's method. So Hammer's method is nothing but an acidic oxidation method in which we have actually used an oxidizing agent KMnO4 along with the combination of acid H2SO4 and H3PO4, in which we actually could obtain an oxidized multi-layer graphene structure. That means a graphitic structure enriched with much oxygen functional group, namely carboxylic, hydroxyl, and carbonyl. So, but how do we confirm whether we were able to extract the graphite structures as such from coal? So, we need characterization techniques. So, to moving on to the first one, structural analysis, I have actually performed Raman analysis. So, a specific characteristic of carbon samples they have got a D band and a G band. So, D band is nothing but defect band, and G band is nothing but as graphitic band. So, defect band would be appearing around 1350 centimeter inverse, and graphitic band would be appearing around 1580 centimeter inverse. So if you just look into the graphitic band of coke and GRO, you can actually observe a little enhancement in the intensity of graphitic band, which actually tells that there is an emergence of graphitic clusters. That means we could able to extract the graphitic clusters from coal. Also, how do you confirm whether oxygen functional groups have been introduced into the graphitic layer? So we have performed elemental analysis using FTR spectroscopy, and again we could observe that the peak intensity due to oxygen functional groups are much intense compared to the precursor coke, again suggests the confirmation of oxidized multi-layer structure. So to our curiosity, we have also performed optical studies and electrochemical studies. So here we showcase the CIA chromatocity diagram, which is nothing but the emission characteristics. So if you look into coke, its emission is actually limited in the blue region. But when you actually prepare the oxidized graphene structure, the emission characteristics has been, it's multi-emissive. The variation range from blue to green yellow region. So it actually tells that we were able to achieve a multi-emissive characteristic of the as synthesized graphite oxide structure. And also from the electrical studies, we have recorded a current potential curve. So that is called CV curve. And if you look into that, the area under the GRO is much higher than that of the precursor, which tells that introduction of oxygen functional group could enhance the active sites and which again contribute to the better performance. So, being a material scientist, our interest would be always in continuous improvement, because we don't want a cradle to grave transformation, because we don't want our research just ending up in our research laboratories or just going into the dustbins. So we just want to have a transformations over there. So for that, we always look into what are the alternatives to enhance the performance of our system. So that's the process where I found it that the heteroatom dot graphene can actually contribute to the enhanced properties. So I think you all know what is the process called as doping. So doping is nothing but an intentional, process of introducing an impurity to the system, any system. But here we're introducing the impurity to the graphitic system, and in that we're actually aiming to modulate or alter the optical or electrochemical properties, not only optical, physical, chemical, all the properties. So there are many studies actually reported that if we have nitrogen, phosphorus, boron, sulfur, all those things, it can actually contribute to a higher electron donor acceptor charges and also can enhance the conductivity. Moreover, the high rich functional groups can contribute to active sites and also multi-emissive properties. But how do you select the dopants? So we have many options, but how you will come across to like one or two dopants? So that's what we are just trying to enhance the properties of the graphene structure. We are not trying to destruct the structure as such. So we have to select the heteroatoms, which is having an atomic radii comparable to that of the carbon atom. And also, instead of having a monodopant, that means instead of having a single atom, if we can introduce two or more, that is a process called as co-doping. It can actually enhance the properties by synergetic effect. Again, you cannot randomly mix any dopants, because in turn it can again contribute to what competing interactions. So that's how I found out that nitrogen and phosphorus, both of them having an atomic radii comparable to that of the carbon atom, would be an apt choice. Moreover, since both of them lying in the same periodic column and also possess a similar electronic structure, it can eliminate the competing interactions, and also it can actually contribute to a multifunctional effect from its coupling activity. So considering all this fact, so from the coke-derived oxide structure, I have actually introduced nitrogen and phosphorus. So if we want to have doping, we should have a nitrogen source and a phosphorus source. So I have used ethylene diamine as a nitrogen source and phosphoric acid as the phosphorus source. So in that, what I was able to achieve, I was able to achieve nitrogen doped sample, which is labeled as Ng, and phosphorus doped sample labeled as Pg, and nitrogen phosphorus co-doped sample labeled as NPG. So again, I have done all the characterization just to confirm whether we'll able to attain the successful doping process. So as I told, the defect band and graphitic band, can you just tell me if it is pure graphene, how the Raman spectra would be? So you have only G band over there. You won't have any significance of D band. So graphitic band is the characteristic of the carbon-based sample, and the defect is nothing but it's actually attributed to the disorder structure in the sample. So here, if you could see that ID by IG ratio that has given here in the left side is nothing but structure. Thereby, there is a substantial increase in the defect densities. And also, just to confirm the elemental composition, again FTR spectra was recorded, and we could observe the characteristic vibrations of nitrogen and phosphorus atoms along with carbon and oxygen, again suggesting the successful doping process. So now to have a comparison between the doping process and electrochemical characteristics, again we have recorded a CV curve. So don't get confused by seeing all these things. Just look into the curve over there. If you could see that which sample was giving a better performance, it is NTGH, if you could see over there. So NTGH is nothing but nitrogen phosphorus co-dope sample, whereas NGH is nitrogen dope sample, PGH is phosphorus dope sample. So when you have both the heteroatoms coming together to the system, we could achieve a better electrochemical characteristics. To quantify that, I have actually calculated electroactive surface area, if you could see in the table. So actually we could see that there is actually 4.5 times increase of electroactive surface area in co-doped samples compared to the undoped or bare sample. Now I have compared. So I have now phosphorus doped sample, nitrogen doped sample, and I have nitrogen phosphorus co-doped sample. So by comparing the systems, I found that if we can have a co-doped sample, there is an enhanced performance due to certain factors. To point out some, it has got high electrochemical surface area. It has also got high synergetic effect. What is synergetic effect as such? The contribution from both the heteroatoms. So these properties as such, if you read out all together, it actually becomes a suitable material for an electrochemical sensor. So we know that there are various types of sensors now available in the market. So electrochemical sensors are nothing but you are recording the chemical information of a sample in terms of electrical signal. So that would be the basic definition to the electrochemical sensor. So I was having a thought that, okay, what would be the apt choice for my analyte for having the electrochemical sensing? So in our society, there is a perpetual misuse of oxytocin happening now. So what is for what purpose it is being exploited? So we'll have a look. So oxytocin is being injected to fruits and vegetables to grow bigger in size, and also to look it very fresh and plump. And also it is being given or injected to cow to produce more milk. And to the worst scenario, it has been also injected to underage girls to make them sexually mature at a faster rate, and then they are pushed into prostitution. So we found that there is a need for the real-time surveillance over this highly abused drug oxytocin. But how can I have the sensing performance of these oxytocin? So for that we should understand its molecular structure. So we found that oxytocin is nothing but consists of a sequence of 9 amino acids. Among that, tyrosine is known to be an electroactive biomolecule. That means electroactive biomolecule means what? By utilizing its redox activity, like oxidation and reduction activity, we will be able to achieve the electrochemical sensing purposes. But again, we have to have a cross check on the existing techniques in the society or in the world now for the detection of oxytocin. Do we have any mechanism for the sensing of oxytocin, or the thing that we develop is much better compared to the other one? So that's a thing I found that we have, yes, we have many systems to detect or sense oxytocin, but most of them are sophisticated. They are expensive or time consuming. So we need a system where actually will be able to promote a real time analysis, the short response time, and there are certain electrochemical sensing work also been reported in the oxytocin part, but again most of them involve tedious electrode fabrications, and it also possesses a very narrower detection range. So my interest was, so far these fossil fuel derived carbon materials are not utilized for these electrochemical sensing purposes. So that's how I found, or I got an interest in, investing the potential of this coke-derived or heteroatom doped sample towards the electrochemical sensing applications. So as I told already, so I have prepared an heteroatom doped coke-based material, and I have utilized it towards the sensing of highly abusive drug oxytocin. So this work has been patented and we also published in the Journal of Food Chemistry. So if you could see in the first curve, what you could observe there, when you recorded the current response of each electrode towards the oxytocin, the maximum current response we could observe was for NPGS, that is nitrogen phosphorus co-dope sample. And also, why would be the reason? So what would be the reason behind that? Again, it is because of the excellent structural or electrochemical active surface area or the elemental compositions involved in the as-built system, which contributed to the better electrochemical sensing applications. Again, we cannot just tell it is being sensed. We should also explore what would be the underlying mechanism involved in that. So again, it has got, I told you that it has got a tyrosine electroactive molecule, but in tyrosine, it has got a phenol group, OH group. So when you are actually giving the electrochemical signals, what happens? It actually been oxidized to a structure called a semiquinone by the loss of 2 electrons, but it is very unstable. So what happened? Immediately it gets transferred to a compound called as hydroquinone, and it is the oxidation potential of this hydroquinone redox species which are observed around 0.3 volts. So I'll move into the previous slide. If you could see that the oxidation potential is observed around 0.3 volt. So there is reason whenever you're performing the electrochemical sensing, your potential vary from different regions for each species. It is truly depend on the electrochemical oxidation potential. So again, we have actually performed the sensing in a range from 0.1 nanomolar to 95 nanomolar, and the as developed sensor could actually give a limit of detection of 0.04 nanomolar, that is nothing but 40 picomolar, was a limit of detection that we could achieve for the developed sensor. Again, there are so many factors that you have to consider when you're fabricating the electrochemical sensor. The first one would be selectivity. Let's say if you're sensing oxytocin, it's not sure that you have the pure oxytocin in the sample. There can be a combination of various foreign species like ions or minerals. So we have actually performed the experiment with oxytocin and also with addition of so many foreign species like ions or mineral species, and we could observe that the as fabricated electrode would give a high selectivity towards oxytocin. Irrespective of the presence of other foreign species, our electrode was able to detect the presence of oxytocin, and also reproducibility. That's a crucial factor in all of our fabrications, because we don't want to get different results different times, right? We have to have the same data or the same analysis every time. So we have actually fabricated 5 electrodes and we have repeated the electrodes multiple of times, and again we could observe or attain a reproducible data. And again, shelf life. So our sample shouldn't be deteriorated after some point of time. So we have actually stored a sample for almost 30 days, fabricated the electrode in 1 week interval, and again repeated the experiments, and again we could find that adequate stability we could observe for our fabricated electrode. So here comes the significance. So I have fabricated the electrode for oxytocin, but what is the significance? The significance comes into the real life sample analysis. So I have actually used fruit juice, milk, human saliva, and human urine for the sensing application of oxytocin. To our surprise, we could actually obtain the electrochemical sensing performance with a relative standard deviation of less than 5%. So coming to the conclusion, that's all, to making all these long stories to short. So my aim, or our aim of the work, was to have a cradle-to-gate transformation of the pollution-causing fossil fuel to a novel course. So here what we have done, we have actually utilized material coal, which is abundant and cheap, and to that we have actually given a value addition by extraction of graphene system from that, and to enhance the performance or to augment the performance, we have actually introduced heteroatoms into the system, and towards the last, so we could actually obtain an application, electrochemical sensing applications towards the highly abusive drug oxytocin. So I think I was able to give a short insight on graphene system or applications. At least if you could, people who's little confused or getting little questions on that, I'll be really happy. So that's all. Thank you.